Hi, welcome to Atomic Structure 2. My name is Dr. English. Today we're going to be talking about electron configuration in the excited state. Specifically, we're going to be looking at revisiting excited versus ground state, relating excited state to Bohr models, and the modern model of the atom. Revisiting excited versus ground state. All of the electron configurations on the periodic table of elements are listed in the ground state. When the atom is energized by an outside source, various electrons will move to higher energy shells further from the nucleus. We can see this in the PhET simulation below. This blue circle represents electrons going from the ground state up to the excited state. When they return down to the ground state, they are releasing a photon of energy, as you can see. We can also see it in the electron energy level as electrons go from the ground state up to the excited state and back down again. The electron configurations listed on the periodic table will appear changed. So for example, beryllium. In the ground state, beryllium is 2-2. 2 electrons in the first shell, 2 electrons in the second shell. In the excited state, we see an electron configuration of 2-1-1. This means an electron from the second shell has jumped up to the third shell. This is an excited state because it does not match the ground state electron configuration. Now this is a very unstable state. Ultimately, these electrons will return to ground state. Let's look at a given. We have potassium with an electron configuration of 2-7-8-2. What is the ground state electron configuration for potassium? So what we would do is go to our reference tables, find our periodic table, look up the symbol for potassium, and say, okay, that's my ground state. So if I do that, the ground state would be 2-8-8-1. Now we're going to compare the ground state electron configuration with the configuration in the given, which is up here. The potassium atom in the given is in which state? Ground state or excited state? If you said excited state, you are correct, because we look at the ground state electron configuration and it's 2-8-8-1. When we look at our given, we see that one of the electrons from the second principal energy level has jumped up to the fourth principal energy level. So if you said excited, you are correct. Excited state. Let's look at a Bohr model of potassium in the ground state versus a Bohr model of potassium in the excited state. We know that in the nucleus of potassium, we're going to have 19 protons and 20 neutrons, and that is in our nucleus. We also know that the ground state electron configuration for potassium is 2-8-8-1. So if I was to draw a Bohr model of this, I'd say, well, in my first principal energy level, I'm going to have 2 electrons. In my second principal energy level, I'm going to have 8 electrons. In my third principal energy level, I'm going to have 8 electrons. And in my outermost principal energy level, my fourth principal energy level, I'm going to have 1 electron, which I know is my valence electrons. We compare that to the excited state of potassium, and we'll use the example from before, where the excited state will be represented as 2-7-8-2. So we still have 19 protons in our nucleus and 20 neutrons in our nucleus. That is not going to change. And in our first shell, we're still going to have 2 electrons in that first principal energy level. But now in our second shell, we're going to have 7 electrons. In our third shell, we'll have 8 electrons. In our fourth shell, we're going to have 2 electrons. So what we can see here is that an electron has jumped from the second principal energy level out to the fourth principal energy level. And as a result, we have a new electron configuration in the excited state of 2-7-8-2. Ground state or excited state. Complete the following table, but assume that everything here is going to be an atom, because that's really important. So we have an electron configuration, we're going to find the element symbol, and then we're going to identify the electron configuration as either in the ground state or the excited state. So I'm going to model the first one. My electron configuration is 2, 7, 2. And I know that all of these numbers represent, well, electrons. So if I add them up, I determine that I have 11 electrons. And since I know that this is an atom, that means that I also have 11 protons. And the number of protons is my atomic number. So my element symbol here for an atomic number of 11 will be Na, which I know is sodium. Now, if I look at this electron configuration and then I go to my reference table and I find sodium, I find that the electron configuration for sodium is 2, 8, 1. So when I compare this electron configuration to the electron configuration listed, I can see that an electron has gone from the second principal energy level up to the third. So this electron configuration is in the excited state in comparison to the electron configuration that is listed on the reference table. Now what I'd like you to do is stop, look at the next 3 electron configurations, determine the number of electrons, protons, the symbol, and then determine whether this electron configuration is in the ground state or the excited state. Welcome back. Let's see how you did. So my electron configuration is 1, 8. So if I add those up, I see that I have 9 electrons. And since this is an atom, that means I also have 9 protons. And when I look up the atomic number for 9, I see that is fluorine, and the symbol for fluorine is F. When I look at my periodic table, I know that the electron configuration for fluorine in the ground state is 2-7. So this electron configuration represented here is in the excited state. Let's look at the next one, 2, 7, 8, 2. If I add these up, I see that I have 19 electrons. Therefore, I also have 19 protons. The element that is represented by the atomic number 19 is potassium, which is K. And the electron configuration for potassium in the ground state is 2, 8, 8, 1. So when I compare this electron configuration to my given electron configuration, again, I can see that this electron configuration is in the excited state. Let's look at our last one, 2, 8, 7. When I add those electrons up, I find that I have 17 electrons. Therefore, I have 17 protons. The element with an atomic number of 17 is chlorine, which is represented as Cl. The ground state electron configuration for chlorine on the periodic table is 2, 8, 7. Therefore, this electron configuration matches my given electron configuration. Therefore, the electron configuration for chlorine is in the ground state. The modern model of the atom, otherwise known as the wave mechanical model or the electron cloud model. This is the most current model for the atom. It is impossible to know the exact position as well as the momentum of an electron at any given instant. They're small, they're fast. By the time you say, hey, look, there's one, it's already gone and probably been in like a million other places. An electron cloud is the best representation of how to visualize where electrons may be found in the atom. An electron cloud can be visualized in terms of a cloud of negative charges around a nucleus. The cloud is most dense where the probability of finding an electron is the highest. The cloud is the least dense where the probability of finding an electron is the lowest. So if we look at this image over here, we can see that the density of electrons are closest to the nucleus. As we move away from the nucleus, the electron cloud becomes less dense. So it is less likely to find an electron out towards the edges of this atom and more likely to find an electron closer to the nucleus of the atom. In the wave mechanical model, or the electron cloud model, the electrons are in orbitals, which are defined as the regions of the most probable electron location, otherwise known as ground state. So if we look at this PhET simulation right here, we can see that every time an electron absorbs energy, it's going to throw out these electron clouds, basically showing the probability of where we might find an electron. Again, we can also look at the electron energy level, showing electrons going from the ground state down here up to either the first principal energy levels or beyond, and then returning back down to ground state. So what did you learn? We revisited excited versus ground state, we related excited state to Bohr models, and we looked at the modern model of the atom. Need more help? Feel free to contact me. Have a great day.